Hello, good evening. I hope my voice is audible and the screen is visible to all of you. We'll go on with the class. Mm, is it fine? Can someone help
Yes,
me? Okay.
yes, sir.
Okay, so welcome back to the NPTEL online course on water and wastewater treatment. So today we'll be solving the questions related to the contents of week 9. And as you all know, the course instructor is Dr. Bhanu Prakash from IIT Roorkee, and I am one of the teaching assistant. My name is Akash Saha, and I am a PMRF scholar at the Department of Civil Engineering at IIT Madras, where I am pursuing my PhD in environmental engineering. So uh, we, we will quickly go through the contents of week 9 lectures. So this week we started off with filtration. What are the different types of filtration mechanisms? The depth filtration mechanism, the surface filtration mechanism, and the different filtration cycles. And then we discussed in detail about the depth filtration. Okay, what are the concept of negative pressures, the single and dual media filters, and what do you mean by backwashing, rate of filtration. So these were all about depth filtration, and then we discussed also about surface filtration, like single media and rapid sand filtration, and then the concept of head loss behind these kind of filters, and different kinds of other characterizations. And after discussing the filtration, we also discussed about the disinfection methods. Okay, like we have also seen some of these aspects in the wastewater treatment, but again we saw some more concepts related to the disinfection part. And at last we discussed about the hardness. Okay, what is the need of softening, what do you mean by hardness, and what are the various formation of complexes and precipitation. So this was the whole overview of the week 9 lectures. So let us solve some uh, theoretical as well as numerical problems based on these concepts. Okay, I see not many people have joined today, but anyway, we'll get along with the class. So the first question, it says that in a water treatment plant, chlorine is added for disinfection. The breakpoint curve is a graphical representation of A, the competing oxidizing agents in the water, chlorine demand of a wastewater, the dose at which free chlorine will be available in the wastewater, and the effectiveness of chlorine in killing bacteria. So which of the options do you think is are correct? So this is about the breakpoint chlorination curve. So which two of these statements do you think are correct?
B and C.
B and C. So that means option B. So yes, that is the correct answer, because if we see chlorine demand, definitely we would be able to know how much chlorine will be required for a particular type of wastewater or water sample, because in the initial uh, phases, some kind of reducing agents or the natural organic matter take up will consume some chlorine. So ultimately, what is the chlorine demand and the dose at which the free chlorine will be available? Okay, the residual chlorine will be equal to the free chlorine. So that time, what is the dose? So that also will become able to know from the breakpoint chlorination curve. So option B and C both are correct. So correct option is B. Okay, let's move on to the next one. Which chloramine is formed when pH range is less than 4.4? Monochloramine, dichloramine, trichloramine, or none of the above? Which chloramine is formed when the pH range is less than 4.4?
Sir, I think B, dichloramine.
B. Any other option? Any other answer? So
Chloramine.
during the formation of chloramines, what do you think? The pH will decrease or increase? And why? Any idea? So we know when ammonia comes in contact with the chlorine, various type of chloramines are forming. So what do you think the pH will be decreasing or increasing? That will give some idea. If you see the reaction NH3 plus Cl2,
Decreasing?
it will be decreasing because the H plus ions will be liberated, right? Because from NH3, one H will come out and the Cl will go and make bond with it. So first NH2Cl will be formed, then NHCl2, and then NCl3. So as more and more chlorine is getting added or getting forming the bond with that
Decrease our ability.
nitrogen, so more and more H plus is coming out. So ultimately the pH will go down. Okay, so pH range less than 4.4 means that pH is too low. So that means the chloramines are forming and the trichloramine have also formed. So you can see that the correct answer would be trichloramine because the pH range is too low. So if you see the detailed answer, we will come to know that the optimal pH for the formation of monochloramine lies somewhere between 7.5 to 9, and under these conditions monochloramine is the main inorganic chloramine. Then dichloramine has maximum formation as the pH of 4 to 6, and while the pH of 4.4 favors the formation of trichloramine. So like that you can remember. So more H plus is getting liberated, so the pH will go down. So less than 4.4, it will be trichloramine. So it's easy way to remember this. Next one. In the membrane filtration, degree of selectivity of membrane largely depends on membrane charge, porosity of the membrane, TDS concentration in raw water, none of the above. Okay, so A and B, both the answers we are getting. What about TDS concentration in raw water? Why do you think it won't affect the selectivity of membrane? Any particular reason of leaving that option? Membrane charge I can understand because based on the electrostatic attraction, some ions will be attracted, some will be repelled. So membrane charge is important. Very well. Porosity also plays a role because based on the pore conditions, the selectivity will happen. What about TDS? How it will affect?
TDS concentration will affect the flux and other things, but I don't know if it'll affect the selectivity.
So see, selectivity, by selectivity, it can also mean that how to tell you? Suppose we have made a membrane. Now divalent, monovalent, trivalent, all kinds of ions are present. Okay, like sulfate is divalent, chloride is monovalent, or you say which one? Some three three charge three negative charge ions are also there. So because of these ions or anions to be specific, the selectivity of other ions will be getting affected, right? Because some ions will be more selective than the other ions because of their charge, because of their hydrated radius, because of their size. Okay, so that will also affect the degree of selectivity of membrane. So TDS concentration also plays a huge role because if more and more TDS is there, then obviously some ions will not be able to go through or maybe return through the membrane. So so all of A, B, and C will play a major role in the selectivity of membrane. Okay.
Isn't it like this TDS, the total dissolved solids, will help the and help in ripening of the filter?
In sorry, in what?
Ripening of the filter, like if we have a clean filter and then we operate, so we will reach to a stage where we rip the filter, meaning that uh,
Ripening of the filter, you mean?
Okay,
yeah,
ripening.
ripening.
Uh, See, actually, ideally, that depends on the type of membrane also. Okay, so basically, if it is dissolved, so mostly ultrafiltration, microfiltration, and yeah, these will not retain any TDS. Okay, the TDS will go through. But yeah, if it is going through nanofiltration, then the divalent charges will be retained. Then again, if it is a reverse osmosis membrane, then the monovalent charges will also be retained. So these things are also will be affecting the retention, or rather the selectivity of the membrane. Okay, what kind of membrane pore size is there?
So
Sorry?
isn't that the membrane charged? Oh,
No,
membrane charge is
no,
different.
no. Membrane charge is another again different. Okay, membrane charge, like what kind of surface functional groups are there. So based on that, they will repel or attract the ions. Okay, so membrane charge also. So there, it is a very complex thing. Many things will interfere based on the size of the pore, based on the charge, based on the type of raw water that is coming to the system. Okay, then fouling can also happen. So all these things will affect the retention or the passage of the pollutants through the membrane. Okay, so all of them will play a major role. That's why before many RO units or reverse osmosis unit, we have a pre-filtration also, because otherwise the TDS will like even the TDS will clog the membrane. Okay, because it will try to retain everything, and a little bit of microorganisms will also cause biofouling. So before membrane also sometimes we have to do some pre-treatment or pre-filtration. Okay, so all these things varies. Okay, I hope it is fine. We'll move to the next problem. If you still have any doubt, you can ask me. Okay. Yeah, so ripening effect is shown here. Okay, observe the graph given below for a filter showing relation between effluent turbidity and the time passed from the start of filter operation. After a duration of 90 hours, which of the following operation would you not suggest in a depth filter? Okay, so change the filter media, backwashing, filtration should be continued, scraping of top layer. And also
So
this,
filtration should be continued.
yeah, so that is the correct answer, because you won't recommend once the effluent turbidity reaches a certain level. Okay, so you can see at the end of around 90 hours, it has the effluent turbidity has started increasing again. So that means we have to stop the filtration there and go for backwashing and cleaning of the filter. And also another thing, this filter ripening, these concepts are related to the depth filters, not to the membrane filtration. Membrane filtration, we have a sheet or a fabric. Okay, so there the concepts are different, whereas depth filters, the concepts are entirely different. Okay, but many of the mechanisms might be same. Okay, but still there is a lot, like this lot many difference are there in these two types of filters. So C is the correct answer. Filtration should be continued. Means you should not suggest this. Next one. Okay, a small numerical. So first the common data is given, then we will see the questions. A sand filter is to be provided in a water treatment plant that caters to a population of 1.5 lakhs. The average water demand is 135 LPCD and the rate of filtration is 12 meter cube per meter square per hour. And the other data is given: the porosity, the coefficient of drag, kinematic viscosity, depth of filter media, specific gravity, and the density of water. Okay, so take a screenshot of this question so that it would be handy for the other parts. Okay, I hope you have taken the screenshot. Just better than noting it down, you just take a screenshot. We will see the first problem. The first problem says if the available surface area of each filter is 35 meters square, then the number of filters required is. Okay, surface area of each filter is given, the number of filters they are asking. Okay, I will go back to the common data. Please try to solve this. We have to find out how many filter beds will be required. Let me know if anyone is solving, or else I'll give you the solution. Okay, I'll wait. Okay, question is, if the available surface area of each filter is 35 meters square, how many number of filters will be required? So whatever the area you are getting, just divide it by 35. You will get your answer. Okay, I'm starting with the solution. You keep trying on. Let's see how it comes up. So first, you have to find out the total water demand. What is the total water demand? Yes, around 70. 70 will come. You are right? But here is one catch which sometimes, like most of the times, you have to do. So I will tell you. So total water demand will be 135 LPCD, okay, into 1.5 lakh people, right? 1.5 lakhs. So it will be around 2050 meter cube per day, or you can also write it as 843.75 meter cube per hour. Okay, so this is total demand. Now, whenever this filtration question comes, we have to also take into account the backwashing requirement. Okay, so that's why it is advisable that 5% of your total water total water requirement you add it for backwash, because for backwashing also we need water. So that water is also added to the total water to be filtered. Okay, so total water to be filtered per day will be nothing but 1.05 times of uh, 843.75. Okay, so it will be 885.9375 meter cube per hour. Okay, so this small thing you have to take into consideration. So the total filtration area required, because rate of filtration is given, so total filtration area required is equal to Q by the rate of filtration. So that is 12. So we'll get something around 73.828. Now each of the filter bed is around 35 meters squared. So number of filter beds will be equal to 73.828 by 35. So you will get something around 2.109. So any value greater than 2 means you have to give approximately 3 filters, 3 beds. Actually, as per this question, if you don't consider this 5% backwash, I think your answer will come out as 2 only. Okay, so this is little tricky, but don't worry, this was a sample problem. So always remember, add that 5% of backwash water, okay, and whatever value you are getting as the final number of filter beds, go for the higher integer, okay, round off to the higher integer. So that many filter beds will be required. Is it fine? Okay. So 3 beds will be required. Next, calculate the settling velocity of the filter media particle having a mean diameter of 0.65 mm. The settling velocity is in millimeter per second. Okay, so you have to find out the settling velocity. The particle diameter is given. So how to calculate the settling velocity? I will show the data again. So please calculate the settling velocity. It's a one line answer. The diameter of the particle was 0.65 mm. 0.65 mm. So how will you calculate the settling velocity?
Uh, Root of 4 into rho g
Yes,
minus 1 into g into
yes,
d
yes. That
divided by
that
3
formula
cd.
you have to use. Okay, no, don't use the Stokes law formula. Okay, because here it is not a laminar condition. So don't use or we don't know, the condition is not given here. Okay, so use the basic equation, the general equation. Don't use the Stokes law equation. So that is the point. So tell me the value.
What is the particle size? Sorry.
0.65 mm. 0.65 mm. 1.51. Is it 1.51? I don't think so. But
Okay, do we have to change the uh, diameter, like from millimeter to something else, or we should keep?
yes, you should change it to meter per second ideally. Ideally,
Okay.
everything. Otherwise, your final answer will be wrong, right? Or, yeah, I think you should change 0.04. This is in meter per second. Yes. Yes. So you will get, actually, it's 0.0487. Okay, in meter per second. So 48.7 mm. So I will just write it here, or rather I will just show you, because it's a direct formula based. So there is no, so correct answer is 48.7 mm. So here you can see the answer you will get is 0.0487. Okay, so whenever in millimeter per second it is asked, it's better to go for more number of decimal points after. Okay, so that you will get a proper answer. Otherwise, your answer would be 40 millimeter per second if you just leave it at 0.04 meter per second. So 48.7 mm per second will be the answer. Right? Next. If the design allows the filtered water for storage to meet the backwashing requirements and the filter bed is required to expand by 0.46 meter, the required backwash velocity is. So now they are asking the backwash velocity, and the filter bed expansion is given as 0.46 meter. 0.46 meter. So just tell me how just tell me what is the approach, if someone wants to. What is the approach, or which equation shall we use to solve this problem? So you have to get the backwash velocity.
Porosity of expanded bed is equal to velocity of backwash by settling velocity, the whole power
Yes,
0.2247
yes. So that is the,
RE.
yeah, Richardson-Zaki equation. So that is called as the Richardson-Zaki equation. So, but for that you need the porosity of the expanded bed. How will you calculate that? Porosity of filter bed is given, but you need to calculate the porosity of the expanded bed. How will you calculate?
You assume we know that the volume of the media is the same
Yes,
before and after expansion.
yes, yes, that is true. So we will solve this. So question number 7. So as you rightly pointed out, the volume of the media will remain same. So that means 1 minus the porosity of the expanded bed into the depth of expanded bed, okay, will remain equal to 1 minus the porosity of the bed into the depth of the filter bed. So that means the total volume will remain the same. Okay, so we will just plug in the values. So this we don't know. DE, that, so our depth of filter was 1 meter and it expanded by 0.46. So our depth of expanded bed will be 1 plus 0.46. So that is 1.46 meters. Okay, so 1.46 will be equal to 1 minus 0.45 is given, and depth of filter is 1. Okay, so from here we will get porosity of the expanded bed 0.625. Okay, so and if I want to apply the Richardson-Zaki equation to get the backwash velocity, then I also need the Reynolds number. Okay, I also need the Reynolds number. So Reynolds number is settling velocity into d by mu. So 0. So in the last question only we have calculated the settling velocity 0.0487 into diameter is 0.65 into 10 to the power minus 3. Okay, and mu is 1.004 into 10 to the power minus 6. So we'll get something around 31.528. Okay, 31.528. So I will just write it down. By Richardson Zaki equation, the expanded bed porosity is equal to the backwash velocity divided by settling velocity to the power 0.2247 into Re Reynolds number to the power 1.0.1. It's a little complex equation, so don't worry. If you put in the values and solve for the backwash velocity, you will get something around 0.01096. Okay, meter per second. Or you can write 10.96 mm per second. Is there any way to calculate the Reynolds number in some other way based on the given equations, given data? Is there any other way to calculate the Reynolds number?
It was based on the diameter, the settling velocity, and I guess the kinematic velocity,
No,
like the times to
that we
Vs
have
and to V.
calculated, right? That we have calculated. I am asking, is there any other way to calculate the Reynolds number based on the data given? This is the generic way because kinematic velocity is nothing but the kinematic viscosity is nothing but the dynamic viscosity by rho, okay, by density. So that is different way. I am asking Reynolds number, can I find in some other way? What other information is given here? Do we note the CD?
Dynamic viscosity is given.
Yeah, that we have used. Do we know the CD, coefficient of drag?
Yes.
So from here, can I get RE? Can I get? Is it possible? Yes, but we should know what is the flow condition, whether it's a laminar flow or what turbulent flow or transition flow. So if it's a laminar flow, you might have seen that CD is equal to 24 by RE, right? If it's a transitional flow, then CD is equal to 24 by RE plus some 3 by root RE plus some point something. So like the three equations are there, right?
Yes, sir.
So from there, but in this, but I'm just giving you options. So like that also you can, if you know the type of flow, it's a, then instead of going for this Reynolds number generic equation, you can also directly calculate from the coefficient of drag if you know the type of flow condition. That should be known. Just to give you another option. Okay. Okay. Now the last part, the head loss in the filter before backwashing is. So what is the head loss in the filter before backwashing? Again, one liner. What is the head loss in the filter before backwashing? Yes, if someone has any doubt, please let me know. How to get the head loss?
It's the rho of the particle minus rho of the water into 1 minus the porosity times to
Yes, yes,
d into the rho of the water.
yeah, that is right. So at last is rho of the particle minus rho of water into 1 minus the porosity into the depth of filter by rho w. Okay, so that is 2.4 minus 1, then again 1 minus 0.45 into 1 by 1. So it is 0.77. That is the head loss. Meter. 0.77 meter. Okay. So this is how you have to calculate. Next problem. That was pretty simple. Consider the following data of a membrane module. A membrane module comprised of several tubular membranes has an effective surface area of 12 meters square. The membrane system is operated in cross flow under a constant flux to yield 1700 liters per hour. The temperature of water is 20 degrees Celsius. Each tubular membrane is 2 meter long and is operated in outside in regime. Assume that dynamic viscosity of water is some number is given. If the tubes have an outer diameter of 3 centimeter, then the number of tubes in each tubular membrane unit are. So you have to find out the number of tubes. So how will you do this? This is a very easy question. If you can visualize the problem, you can find the solution. If you cannot visualize, it will be difficult for you. Are you able to understand what is given in the problem? What is meant by outside in regime, and what is the flux and the effective surface area? Any idea about what this problem is? Do you know what is a tubular membrane? Any idea? Because membrane, we always assume it to be a sheet membrane, like a filter paper, a flat sheet membrane. But it is here it is mentioned as tubular membrane. So what is the shape of a tubular membrane?
Cylinder?
Cylinder, yes. And yeah, so can some can you tell me like how to approach, like how to find out the number of tubes?
N into pi d square by 4.
Okay, so you are saying
Um,
pi d square 4. So that's why I was telling you have to visualize the problem. Okay, so let me tell you. Okay, so let me tell you. So generally what happens, suppose we have a membrane like this. Okay, we have a membrane, water is flowing from the top. Okay, it has so many pores, n number of pores are there, I don't know. Okay, then from inside this it will go and filter out. Okay, so I am telling you this is a flat sheet membrane through which water is passing. Now instead of a flat sheet membrane, if I roll this into a kind of tubular membrane. Okay, so this is a tubular membrane where water can either pass across this. Okay, but that pass across this means water will come from outside, go inside the tube and go like this, or it can go like this. Okay, water is coming from the outside, going through the surface, like how should I tell you, uh, just, so water is going through this. Okay, will go through the surface area of this throughout this cylinder. Let's suppose this is a cylinder, and go inside and flow through the membrane. Okay, like that. This is one. This is known as outside in. Outside in. From outside it is going in. Otherwise, what can happen? The water can flow through this membrane, okay, and come out like this. So this is inside out. So this is inside out. Now you should also know that this tubular membrane will have some thickness, right? So if you make it more properly, it will be something like this. Okay, so there will be, this will be my outer diameter. Okay, and this small one will be my inner diameter, right? Now let me ask you, if water is flowing inside out, what will be my surface area? So in the flat sheet membrane, the surface area will be the area of this sheet, right? Length into breadth. That will be my area, length into breadth. But when the water is flowing inside in or outside in, sorry, inside out or outside in, what will be my surface area?
So because it's outside in,
Okay.
then we have to take this outer diameter into the
Yes,
length.
you will take the outer diameter. Okay, and what area will you take? Will it be a area of circle or area of something else?
A circle.
No, no. So now see, just try to visualize. Suppose outside in is happening. Okay, so water will have all this surface, right? All this surface area to go through from all the sides, and inside it
So
will flow. So that
also
means,
length will be calculated, sir. Also
sorry.
length, also length will be calculated, tube
Yes,
length.
yes, yes. Let's say the length is some L. Length is some L. Okay. And outer diameter I will mark it as capital D. Inner diameter I will mark it as small d. So if it is outside in, my effective surface area through which the water can come inside will be pi dl. Does that make sense? The surface area of a cylinder. What is the surface area of the cylinder without the top and the bottom? It is pi dl, right? Are you able to visualize? So suppose this is cylinder, the water can flow through anywhere in the surface area throughout the length. Okay, and this surface area will be equal to pi dl. But if it is, a inside out configuration, then my surface area will be pi small dl, because now it will have a little lesser diameter. Okay, because it is flowing from the inside to outside. So
Inner dia.
inner dia. So it will be small pi dl. Is this clear to all of you? Are you able to understand?
Yes, sir.
Okay. So this thing. So here the area of the circle will not come into the picture. Okay, because water is flowing through the membrane on the outer side. Okay. So the entire surface area will be taking. So these are basically called as hollow fiber membranes. We call them as hollow fiber membrane. And what happens is we have a big unit. Okay, we have a big cylindrical unit, and suppose this is the top and then, and there will be so many small tubular units like this. Okay, small fibers, hollow fibers, which we call them, it will be there. So what will happen? The water will flow through this membrane and it will come out like this. Okay, it will flow through this, come out like this.
Sir, just like a condenser.
Yeah, you can say. Okay, so the configuration is like this. And one more thing, are you aware of dead end filtration and cross flow filtration? Are you guys aware of this?
Yes.
Okay, so where do you think the fouling will be lesser, in dead end or in cross flow?
Cross flow.
Cross flow it will be, because it will be flowing parallelly. Okay, so mostly these hollow fiber membranes are cross flow filtration membranes. Okay, so like that. So now coming back to the question, now if we go back to the question, now tell me, how will you solve this? So here you can see, if the tubes have an outer diameter. So outer diameter is given because this is operated in an outside in regime. Okay, outside in regime is given. So that's why the outer diameter is given. Outer diameter is given. Otherwise, the inner diameter would have been given. Or sometimes they will give you both the diameters. You have to analyze which one is the right option.
So you said A equals to pi into D into L. So
Yes.
pi is 3.14 times to D. You've given us in centimeters. I guess we will
Yeah.
convert this to meter, which
Yes.
is 0.03
Yes.
times to L is 2 meters long. So it's 0.1884. This
Yes.
is for one tube.
This is for one tube. And the entire
Now,
effective surface area you need is 12 meters square. Right?
yeah, so 12 divided by 0.1884.
Yeah. How much you are
Yeah,
getting?
I guess it's 63.
Yeah. So you will have some 64. So just increase it to the next number. So the correct answer is 64. So that's how you have to do it. Okay. So very simple calculation. Calculation wise, don't worry. It's just you have to visualize how the water is flowing. Because if you're not able to visualize, then you will be selecting some wrong surface area. Okay, so the surface area visualization is very important here. Okay, here many extra information is given. Flux is given, viscosity is given, temperature is given. We don't need all these things. So can someone tell me what is flux? What is flux?
Flux is the volume of liquid that will pass through surface area in
Okay,
time, in a particular time.
per unit time, yeah. So amount, so here if you see the constant flux to yield, it is given liters per hour. Okay, so generally flux is not in liters per hour, it is liters per meter square per hour. Okay, so that area term is also important. So they might have considered it to be 1 meter square area. So generally we don't depict the flux as liters per hour. It will always be liters per meter square per hour. We generally denote it by LMH. LMH. Okay, so that is the case. Okay, moving on to the next problem. It says that clean water at 20 degrees Celsius is passed through a bed of uniform sand at a filtering velocity of 5 meter per hour. The sand grains are 0.4 millimeter in diameter with a shape factor of 0.85 and a specific gravity of 2.65. The depth of the bed is 0.67 meter and porosity is zero point 0.4. Determine the head loss through the bed. So you have to use Karman-Kozny equation. So are you aware of this equation, or shall I directly give you the solution? Are you aware of this Karman-Kozny equation? So this is somewhat related to the previous problem only, but they are asking to use different equation here. I think you are not aware. So HF is equal to friction factor into length into 1 minus void ratio into Vs square by void ratio cube G into diameter. Are you aware of this equation? No?
No, sir.
No. Okay, I will give you this. So this is, so mostly many places this head loss are generally calculated through many empirical equations. Okay, so like the firefighting fire demand, okay, fire water demand, there are so many empirical equations. So here also there are many empirical equations based on the various circumstances. So they will generally mention which formula to use. So this is another method which we call as Karman-Kozny. So let's see how to solve this problem. So for this, to solve this, this is, I think, question number 10. Okay, so Karman-Kozny equation. So HF will be equal to F dash, that is a friction factor, into the length or the depth of the filter. 1 minus E is the porosity into the filtering velocity square divided by E cube G into diameter of the particle. Okay, so HF here is called as the friction factor, and this friction factor HF is equal to 150 into 1 minus E by RE plus 1.75. Okay, simple calculation, but and L is the filter depth, E is the E is E is not the void ratio, E is the porosity. I was making a mistake. E is the porosity, because many places we denote E by void ratio, but here E is the porosity. You can also write it as M, that doesn't matter. Okay, FVS is the filtering velocity, and dP is the diameter of particle. So particle diameter. Okay, so one more thing you might have analyzed is that there was something known as shape factor. So where do you think the shape factor will come into the picture? Why do you think we need something called as shape factor? Any idea? How will it affect?
Because spherical particles will behave in a certain way
Yes.
in the wastewater,
Yes.
and
So whatever derivation that we do, we assume that the particle to be spherical, but most of the times the particles are not as perfect sphere. So that's why we denote something known as shape factor to take that into account, so that the settling velocity or the Reynolds number can be decreased in that factor. Okay, so like that. So for this question, we need to first calculate the Reynolds number. So Reynolds number, we will just simply, so we know it is rho Vs into d by mu, right? So instead of that, we will just add the shape factor into this. So this is the shape factor. So 0.85 into 998.2 kg per meter cube for your density. Filtering velocity is zero point 0.4, and then diameter is, oh sorry, filtering velocity is 1.39 meter cube per second, and your diameter is zero point 0.4 mm, so 4 into 10 to the power minus 4 meter, divided by mu is 1.022 into 10 to the power minus 3 kg per meter second. So if you solve this, you will get 0.47. So this is less than 1, that means it is laminar flow condition. Okay, laminar condition. So my friction factor F will be equal to 150, 1 minus 0.4, that is the porosity, divided by the Reynolds number plus 1.75. So 193.24. So ultimately my head loss, so friction factor into the depth of the bed 0.67 then 1 minus porosity into the filtering velocity square divided by porosity cube into G into the diameter of particle. So 0.6 meter. Okay. I hope this is clear to all of you. Now, all these questions that we were solving, we were assuming that the filter bed, suppose this is my filter bed, it is having only a single type of particle. Okay, single type of particle. Water is flowing through. So it is having a single. But do you think ideally this is the case in all the filters? Do we have a uniform sized particles throughout the filter? Is it so?
No,
No.
if we have kind of
Yeah.
layered filters, it will be different.
Yes. So we have different layers generally, dual media or triple media. Okay. So each layer will have their own average particle size. Okay. Let me say it as Dij. Okay. So it will be different D1, D2, D3 like that. And also the mass fractions will be different. Some x1, x2. Okay. How much mass it is present. So generally, this kind of problem where we have to calculate the head loss, there can be questions where the mass fraction and the diameter of the particle is changing. Okay, so for that also we have to do similar method. It's just that I will just show you the question. So uh, same question like before, but here the mass fraction and the average size of the particles are also given. Okay. So passing and retent, that information you need not worry, but that is the sieve uh, retention size is given. But you can see that various mass fractions and the average size of the particular fraction is given. So like that, there can be question of filter media of different types of like particles. This we call as non-uniform stratified particles. Okay, the earlier one was the uniform size particles. This is known as non-uniform stratified types of particles. So I'm not solving the question now. I'm just telling you that these kind of things are also there. Okay, we can calculate it. The same equations are there, formula is there, so you need not worry. Just layer by layer we have to solve. We have to solve for each of the layer and then add it. Okay. If any one of you is more interested, then I can give you the solution maybe through mail. Okay, just let me know if you are interested to find out. Okay, next water. So again, uniform bed water question, but here it is also given that the filter medium is to be expanded to a porosity of 0.7 by hydraulic backwash. Determine the required backwash velocity and the resulting expanded depth. Okay, can you calculate? We have seen a similar problem, so let us skip it for now because exact similar problem we have already seen. So porosity, expanded depth porosity is directly given. You have to find out the backwash velocity. You can use the Richardson-Zaki equation and also the expanded depth. Okay, so both the things you can calculate. So I'm skipping it for now. Okay, let's solve some direct questions. Which of the following are the mechanisms of depth filtration? Interception, sedimentation, impaction, photodegradation, flocculation, mechanical screening. Which of the following are the mechanisms of dust filtration? Any other answer? So only two mechanisms, A and B.
Well, in the videos, the teacher was saying like it's interception, diffusion, and sedimentation.
Okay. What about impaction? Have you heard about impaction? And can flocculation also take place? What about photodegradation? So ideally, for the mechanisms of, if we talk in terms of only depth filtration, except photodegradation, everything can happen. Okay, so except the photodegradation, everything can happen as a mechanism of depth filtration. So all of them are the correct answer. Okay, so impaction is nothing but if the media is not able to flow because of its own inertia and it is getting deviated. Okay, so interception, as the name says, sedimentation, impaction, flocculation we have seen, and mechanical screening. Everything will happen in depth filtration. Okay. Yeah, so all these are given, all the explanation of given, except photodegradation. Photodegradation may happen, but it is not the mechanism of depth filtration. Okay, if light intensity of some UV treatment is there and some photocatalytic material is there, then photodegradation may happen in the filter media, but that is not a innate mechanism of depth filtration. So that's what you have to remember. Which of the following statements are or is true for granular media filtration? Head loss decreases with increase in time of operation. Filter lightning occurs in 24 hours. Head loss increases with increase in time of operation. None of the above.
Sir, C. Head loss increase, which increase in time of operation.
Yeah. So head loss increases with the increase in time of operation. That is true because more and more we do the filtration, the pressure head increases. Okay, so head loss will increase. Next, there are two statements regarding the backwashing of rapid gravity filters. Backwash velocity must be lower than the settling velocity of the smallest media particle. Total volume of media bed as well as volume of media solids increases during the backwashing. So what will happen if the backwash velocity is more than the settling velocity of the smallest media particle? What will happen?
That media that has been formed will be washed out
Yes, yes. So that's why it should be lower than. So statement 1 is true. And what about statement 2? Why it is wrong?
because the volume of media solids will stay constant.
will remain the same. Yeah, the volume of the media solids will always remain the same. Total volume of media weight can increase or decrease, but the volume of media solids will remain the same. Okay. Next, which of the following statements are not correct? Smooth stack layer is formed in slow sand filter, increases the quality of filtration, takes around 1 hour to get formed and after being scraped while cleaning the filter, formed by the process of biological metabolism by microorganisms. So yes, A and C are correct. Okay, this is very simple because fruit are formed in slow sand filter and it doesn't take around more or it takes much. Okay, so moving forward. Okay, so membrane equation question is given. Calculate the percentage recovery and TDS rejection for a reverse osmosis unit with the following data. Feed water flow rate is 2300 meter cube per day. Retentant flow rate is 600 meter cube per day. TDS in feed water is 800 milligram per liter. TDS in permeate is 80 milligram per liter. So find out the percentage recovery and the TDS rejection. Please calculate. Any idea how to calculate this?
Subtract the retentate from feed water and calculate how much is the percentage recovered,
Yeah,
and then multiply it.
yeah, that is fine. That will be your percentage recovery. What will be the TDS rejection? What will be the TDS rejection?
So TDS rejection will be in flow rate or um, sorry, I think it should be retentate flow rate into um,
Yeah.
the
So what do you mean by
TDS.
rejection? Like how much percentage of the TDS is being rejected, right? Rejected by means by the membrane. So the data is given, feed water and permeate is given. So you can calculate. Okay, so generally what we do is, just a second. 1 minute. Yeah. So generally the schematic of any membrane unit, we show it like this. Okay, this is how we show a membrane. Okay, this defines the membrane part. So suppose we have a feed, let's say QF, it is 2300 meter cube per day. Okay, it will pass through the membrane and some part will come as permeate, which will pass through the membrane. It will come out as membrane, and some part will go as reject because we generally show it as for a cross flow thing. So some part will go as the reject. So that is also given in the question, QR. So this is 600 meter cube per day. So now we can calculate this QP. What will be my permeate? It will be nothing but 2300 minus 600. So that is 1700 meter cube per day. So first question was percentage recovery. So by percentage recovery, I mean like how much water I am able to get from the feed. Okay, if my feed is 2300, I am able to get 1700 as my permeate. So it is nothing but QP by QF into 100. So 1700 by 2300 into 100, it will be 73.9. Now the next problem says that how much is getting rejected. Okay, TDS rejection. TDS rejection. So rejection is always in terms of the contaminant or the particle or the pollutant we are checking out. Okay, so let's say the concentration of any pollutant or feed is around 800 milligram per liter. Okay, and in the question it is given that the concentration of the permeate is Cp, that is given as 80. So from 80 milligram per liter, the Cp is coming down to, from 800 milligram per liter, the permeate concentration is only 80 milligram per liter. So what will be my TDS rejection? How much is getting rejected? So this is nothing but 1 minus Cp by Cf. Does that make sense? Okay, recovery is permeate by feed, but rejection is permeate by 1 minus permeate by feed. So that by 1 minus Cp by Cs. So this is 90%. So 90% of the particles are getting rejected by the membrane. Can someone tell me what will be my CR? What will be my CR? Can someone tell me? CF is 800, CP is 80. What will be my CR?
Is it like mass flow?
Sorry? Please say it
Is,
again.
is it like mass flow? You have to do CR is equal to QF into CF plus QP into CP
Will it be plus or minus?
minus.
Minus, yeah, because that part is going out. So right, do the mass flow. So just don't make the mistake of writing it as 800 minus 80. Okay, 800 minus 80 will not give you the answer. Okay, generally the CR is very high. The reject concentration will be very high. So if you see, so we know if we do the mass balance, QF into CF, right, will be equal to QP CP plus QR into CR. So if you do this, you will get the answer. So from here you have to find out the CR. So it will be QF CF minus QP CP by QR will give you the CR. Okay. How much is it coming? Did someone calculate? Can you please tell me what is the answer? What is the CR? Someone please calculate and let me know. I just want to show you like how big the value will be. What is the value of CR? Yeah. So around 3000. So roughly around 3000 it is coming. So you can see that how much concentrated it is becoming. So that's why we call it as either reject or concentrate, because the value is very high. Okay, it will be very high. So like that. But if you write 800 minus 80, so 720 will be too less for the reject. Okay, let's move on. One thing, we have done this already. So I am just skipping the question, the type of questions which we have already done. Anyway, you will get this. Just a second. Dialysis in our kidneys is, it is a concentration driven value. Yes, that is correct. If the raw water turbidity is less than 10 NTU, then which of the following treatment trail will be favorable? What is the answer? B. Yeah, B is the correct answer. But if it is more than 10 NTU, then what will be the answer? If it is more than 10 NTU or 50 NTU like that, then A. Yes, then sedimentation will also be coming to the picture. Yes. If a sand media has uniformly distributed particle size, then it is best suited for which of the following? It is suitable for a rapid sand filter. Okay, because for uniformly distributed particle size, we generally go for a rapid sand filter, not a slow sand filter. Because slow sand, you need more closely packed pore size. So uniformly distributed won't help. Looking at the following picture after 90 hours of duration, which of the following operation would you suggest in the depth filter? Change of filter media, backwashing, filtration should be continued, or scraping of top layer? Here the correct answer will be, so after 90 hours, the run has to be terminated because the effluent turbidity has increased. So we have to backwash. We have to go for backwash. Not scraping the top layer directly, we will first go for the backwash. Okay. The separation limit for a membrane is determined by the lowest dash that can be separated. Lowest dash that can be separated. What will be the answer? So the answer is yes, molecular weight. So membranes we generally define not in terms of uh, pore size, we generally define in terms of molecular weight cutoff. Okay, MWCO, molecular weight cutoff. Whether it's 100 kilodalton or 1000 kilodalton, 10 kilodalton, we generally decide the separation limit as per molecular weight cutoff. Okay, yes. So last question we will do for today. A filter is backwashed as 50 meter per hour at 15 degrees Celsius. Determine whether the 0.1 mm diameter particle of sand will be washed from the filter. Very simple problem is given, like simple to understand. You have to tell me how do we approach this problem. A filter is backwashed at 50 meter per hour. You have to tell me whether a zero point 0.1 mm diameter particle will be washed from the filter or not. How will you do calculate this? Forget everything what you have learned about backwashing or depth filtration, whatever you have learned, forget it. Just by basic physics concept, how will you solve this?
The settling velocity of the particle uh,
Okay.
should be less than the
Yes,
backwash
settling
velocity.
velocity, that is true. You have found, so you have learned about settling velocity, but what is the more basic way to find it out? Settling velocity, obviously, we will check the settling velocity, but more simpler way. If you don't know, suppose you have not learned about settling velocity, then how will you do this? Because settling velocity also, through some concepts only you are deriving the settling velocity. What are those concepts? Do you remember how you are deriving the settling velocity? What are the assumptions, or how do we derive the settling velocity? Do you remember, for Stokes law or whatever? Because if you are talking about settling velocity, I don't know which condition it is, whether it's a laminar condition or transitional condition. How will you calculate the settling velocity? What are the basic concepts behind the settling velocity? Well, I'm just asking you to think, because we can solve it through that way, but still, what is the basis of the derivation of settling velocity? Just to give you one thought, that's why this question is there. So, okay, suppose a particle is there in a liquid media. What are the forces acting on this particle? What are the forces acting on this particle?
The buoyancy, the drag, and the gravity.
Yes. So you have told me. So one is the gravitational force, right? One is the force of buoyancy, okay, and another is the force of drag. Okay. So like this. So if I equate all this, okay, and find out the, so suppose force of gravity plus force of buoyancy plus force of drag, but this will be in opposite directions. I am putting minus. So ultimately, if I get a positive value, that means the particle is going down. If I get a negative value, that means the particle is going up. So that is the basic concept even for the settling velocity. If you remember, we equate the total mass into acceleration with some, so mass into acceleration, that force we will equate to the other gravitational, all these forces, to come up for the equation of settling velocity. Okay, so that is the idea behind this question. So what is the, how can we calculate the gravitational force? What is the formula? So this is basic physics that I am asking. What is the formula? Okay, what is the formula for F? Force is equal to second's law of Newton. F is equal to
Mass into acceleration.
mass into acceleration. Okay, so now gravitational force will be equal to, so instead of A, I can write G, M into G,
And 1 into mu by r squared.
R square.
Yes, that was the gravitational force, if I'm not
Okay.
wrong.
No. I am not. So you don't have to substitute anything. So G will remain as a mass. You can write it as density of the particle. Okay, density of the particle into the volume of the particle, because these are generally known. Mass is not given generally in the problem. So density or the diameter. So from diameter you can calculate the volume of the particle into G. Okay. So what will be the density, diameter of the part, sorry, volume of the particle? It will be pi by 6 dq. Okay, pi by 6 dq into the G. So like that you can calculate the gravitational force. What will be my buoyancy force? What will be the buoyancy force? You have just calculated the gravity. What will be the buoyancy force? What will change in buoyancy force? G will remain as it is, right? Buoyancy force G will not change. G will remain as it is. The particle will be same, right? It is acting on that particle. So what will change? The density will change. Okay, the density will change. So it will just become rho of water. Rho of water into particle volume into G. Does that make sense? So that's how we calculate the buoyancy force. What will be the drag force? What will be the drag force? We have calculated in the previous class, I think, or somewhere. I don't remember. What is the drag force? No one? Half? Now can you tell me half?
Rho v, the coefficient of drag, and something like these.
Yes. So half CD rho W into projected area into Vs square, right? VA square or VB square, whatever. Okay. Is this one? So here the velocity that we will use is for the backwash velocity. So instead of the settling velocity, because that backwash is dragging it, right? So instead of the settling velocity, we will use the backwash velocity, whatever is given in the problem. Okay. What is the projected area here? What is the projected area for drag?
Pi d square by 4.
By 4. The area of a circle. Because if we have a sphere, okay, if you have a sphere, from the bottom it will look like a circle, right? From the bottom it will look like a circle. I'll just, So it will be pi 4 d square. Okay, CD you can calculate by that Reynolds number. Okay, very simple Reynolds number. We can calculate the CD, and we all know this. So once you equate everything, you calculate FG minus FB minus FD. Once you calculate this, you will finally get whether it's positive or negative, and based on that, whether the particle will be thrown out of the system or will be in the system. Okay, so simple physics equations which you know you have solved, but how to apply it in a problem.
Sir,
Yeah,
the drag force formula is like F D equals to the half rho V square CD into A. And you have divided the V square again
oh, sorry,
into
sorry. Yeah, yeah.
2.
By 2 will not come. Sorry. Yeah, I made a mistake. Yes. By 2 will not come. Yeah. Sorry. It will be half CD. Okay. Sorry. Okay. I hope this problem was interesting. Something to think about. Yeah. So that's all for today from my side. We'll meet again on 31st. Uh, One more thing. Yeah. 31st, I may be busy during this time. So will it be fine if I keep the class on Monday, 7 to 9? Will it be okay?
Yeah.
I'm good too.
Yeah. Okay. So in case the timings are getting changed, you will get a mail. Okay, we will get a mail properly. I'm not 100% sure now, but in case if the timing got changed, I will you will be informed. Okay, so 7 to 9, same time. Time we will keep the same, only the date will change. Okay. So yeah, that's all from my side for today. If you don't have any more queries, you can leave the session. Thank you so much.
Sir, I
Yeah,
have one question.
yeah,
Um, so if we for groundwater especially, um, the water doesn't have any suspended solids, right? The water wouldn't have suspended solids. It will
J-
have more of dissolved solids.
yes, yes.
So if we are thinking for treatment of groundwater, which has high hardness, for example, um, what would be the influent quality if we have to use the membranes? Would it be, is it like if it has high TDS, it should have a pre-treatment, or is it you can use it directly?
Yeah, so generally this if hardness is very high, then yeah, scaling will cause some problems. Okay, so depends on the type of membrane. If you are directly going for reverse osmosis or the nanofiltration, then the problem will be there. But if you are just going for ultrafiltration or microfiltration, then the problem will not be there. Otherwise, for RO and all, you have to do some pre-treatment. You have to remove the hardness, because if you know RO, it will remove everything, even the monovalent. So hardness is divalent. It will also be removed. Even for nanofiltration, also the divalent ions will be removed. So if it is getting removed, if it is not getting passed through the membranes, it will try to clog the membrane. Okay,
Okay.
inorganic scaling will happen. So by the help of some alum or some other techniques, you have to remove the hardness. You have to decrease the TDS and then go for the membrane unit.
Okay.
Okay. Any other doubt? Someone will also was raising their hand.
No, sir. No, sir.
Okay. Are these sessions helpful for all of you? Is this like, are you getting any
Yes, sure.
help?
Sure, sir. It is helpful.
Okay.
Thank you.
Yeah, good, sir.
Yeah, thank you so much. If you need any other concepts or anything that you want me to discuss specifically, you just write a mail to me so that in the next class I can go through that. Okay, instead of solving all questions, maybe we can discuss some concepts also, so that I will prepare some slides and then we can discuss it more effectively. Okay.
Sir, the questions in exam will be like the ones that we're working here or in
Yeah,
the
yeah.
assignments.
So the ones which we are doing for this like multiple choice problems, that will be there. Some subjective problems which I am taking extra, that big problem, those big problems will not come. Ideally, it should not come. But just to give you a larger idea, okay, some more perspective regarding the type of concepts or problem that can be asked, I am solving some more subjective problem. Like the last problem which I showed you, ideally it won't be asked, okay, because three levels of calculation is there. uh, but individually those individual calculations can be asked as a multiple choice. So that is the idea behind it. Okay, but the questions that we are solving are related to your syllabus and related to your particular type of questions that you may face in the final exam. Okay. But since what I have realized is many of the people are also preparing for some gate exam or some SSC exam, some things. So that's why I'm going a bit beyond the level of problems on the harder side, but it will be like this only. Okay. Yeah. Thank you so much.
Okay, thank you, sir.
Yeah, thank you. You can leave the session if you don't have any more queries. Yeah.